But let's keep going with our conversation about reaction types, and let's talk about single replacement reactions now. So there are two different types of replacement reactions. Single replacement are the first type. Now, before we get into this, I would like to draw your attention to your note packet, specifically the back of your note packet. I mean the back page. If you look here, there's this thing on the back. This is called the activity series. You should be looking at this, maybe flipping back and forth, because we are going to be using this activity series. What it's for is for single replacement reactions. So single replacement reactions look like this. We have some element A reacting with some element By. And what we're going to do is we are going to form AY and B. Now, if you notice what's occurring here is that we have a free element, or in other words, an element by itself, is reacting with a compound that has a less active element on it. And what it does is it releases the less active element. So as you can see here, A is swooping in and it's kicking B out, and B is being let free. So B is being replaced. You can think of this in a positive way or a negative way. I don't know how you'd like to think of it. Think of it as in like A is cutting in and stealing B's partner, like at a dance or something, or maybe A is swooping in and helping B out, and whoo, B is out of there, right? So they are replacing no matter what, right? That is what we call single replacement. And single replacement is based on the activity series. So if you look at the activity series, take a second, look at it along with me on the back of your note packet. The activity series has a bunch of things listed on two different columns. So in other words, the way that you can kind of interpret this is that similar things replace similar things, meaning that metals replace metals and halogens replace halogens. Now, the way that the activity series works, if you look at the definition, it says a free element replaces a less active element. The lower you go on the table, the less active you are. So in other words, lithium, who's at the top of the table, can replace anything below it. Anything. Whereas gold, who's at the bottom of the table, can't replace anything. It can't replace because it's at the bottom. So if I were to ask you, like, could zinc replace nickel? You would look and say, yes, of course it could. Zinc is higher than nickel on the activity series. An analogy that we sometimes use in chemistry that I've heard very often is upperclassmen. Think of it like seniors and freshmen, I guess. Upperclassmen can kick out lowerclassmen, but lowerclassmen can't kick out upperclassmen. That's just a thing that I've heard very often. I don't know if that works for you, but maybe take it with you. It might help you out. So things lower on the activity series can't replace things that are higher. The things that are higher can replace anything below it. And again, metals replace metals, halogens replace halogens. Let's do a little practice so you can see what this looks like. This is actually a pretty easy reaction type. So as long as you try. Let's look at zinc, and we are going to react zinc with copper 2 chloride. Now, the thing that we have to do first and foremost is check to see if the reaction even works. So go back and look at your activity series and look to see if you can find zinc and look to see if you can find copper. So can zinc replace copper? Well, if we look, yeah, it can. Zinc is above copper. If it couldn't, we don't have to do anything. Shoot, we're done. We just write no reaction and we move on. But zinc, which is a solid, can replace copper. Notice that it says a solution of copper chloride, which means that this is going to be aqueous, right? So this is copper chloride, and it is aqueous. And again, what we're doing here is the zinc is swooping in, and it's replacing the copper, and the copper is being set free. So our new product is zinc chloride. Now keep in mind that the Cl2 isn't a Cl2 because of chlorine, and it's not because it's a Hofbrinkel, but because both copper and zinc have a +2 charge. The subscripts aren't always going to be the same. Sometimes they'll change. The only time subscripts are ever ported over directly is if it's a polyatomic. Now, The thing that is let free is copper metal. And this is balanced, so we don't have to do anything. Okay? And that's it. That's single replacement. You just knock something off and you replace it with something else. Let's try another one. Let's see. I got to get to my other example here. I got to flip my page. So what if we did something that was between sodium and magnesium bromide? So sodium and magnesium bromide. First, check that activity series. See if it even works. If it doesn't work, you can stop. But sodium is, in fact, more active than magnesium, so we get to do our thing, right? Why don't you write it out? Try it out. I'll pause, and you come back and let me know how you do. Hopefully this is what you got, bones and all. That means, we also balanced it. So notice that I wasn't lying to you before when I said that sometimes the subscripts don't transfer over, right? The bromine is a 2 on the left side, but there's only one bromine on the right. This is because the charge balance is different. The ratio between the two is different. Magnesium and bromine is a 1-to-2 ratio, whereas sodium and bromine is a 1-to-1. So please keep that in mind. Please make sure that when you form new compounds, you balance the charges again, because you have to do it every time. It doesn't just pull it over. You gotta be careful. Let's look at another one. Let's look at the balanced equation between, how about fluorine and lithium chloride. Now in this situation, we are dealing with a halogen. So we don't replace metals this time. We're going to replace the halogen. So lithium chloride, LiCl. So we are not going to replace the lithium with the fluorine. This time we are replacing the chlorine with the fluorine. And does this even occur? Look at your activity series. Yes, indeed it does. So that means we get lithium fluoride. Hold on. Took me a second to figure out what I needed to write. Lithium fluoride and chlorine as a gas by itself. Remember, it's one of those Hofbrinkel diatomics. So we have to balance this real quick by putting a 2 here and a 2 there, and we're good. Okay, so remember, similar things replace similar things. Metals replace metals, halogens replace halogens. Just refer to the table. They're separate groups, but on the same table. Let's look at something a little different this time. What if we took magnesium and we reacted it with what we call hydrochloric acid? Now, hydrochloric acid is a common used acid in the laboratory, and the formula for hydrochloric acid is HCl. So, here's what I want to show you here. When we have a metal reacting with an acid, oftentimes what we're looking to see here, the magnesium's not going to replace the chlorine, but instead now we are going to treat the hydrogen as the thing that's being replaced. And your activity series actually has a little clue. Do you notice how in the activity series there's a big, bold, capital hydrogen? That's because hydrogen can also be replaced if you have a metal that's active enough. Magnesium's up to snuff, it's active enough, so it is going to replace, and we get a solid magnesium chloride, or excuse me, we get an aqueous magnesium chloride, and we get a hydrogen gas, which is somewhat explosive. So this is a somewhat violent reaction. So if we did this, that's how we do it. Now, we also need to put a 2 here. One more little example. We could do the same thing if we have something like potassium, and it's reacting in a solution of water. So in this situation, we have potassium, which is just a solid, and we're reacting with H2O, which is a liquid in this, or it says a solution of water, doesn't it? So then I guess we'll put aqueous. And we want to ask ourselves, does potassium replace hydrogen? But when you have a situation like this, it's easier to do like we did before, where you kind of open up the water and you pretend that it's HOH, because that allows you to see that the potassium is going to replace the hydrogen, and the hydrogen is going to be released and set free, because potassium is active enough, right? So we are resulting in KOH, which is aqueous, and we get more of that hydrogen gas, which is explosive. So this is a violent reaction. This is why, what's the word I'm looking for? Alkali metals, so anything in the group 1 metal, they're highly reactive in water. They're somewhat violent in water, actually. So the lower you get on the table, so like potassium, so even like rubidium, cesium definitely, they start reacting violently in water. Francium can't even be in moisture, it just explodes. So you got to be careful with those types of metals. And this is why, because when they react with water, they are active enough that they kick the hydrogen out and they form this hydrogen gas, which can be really dangerous. And that's it. That's single replacement. We'll see you next time for double replacement.